We present Monkey See, Monkey Do, a framework that uncovers the roles of attention elements in intricate human motion patterns and leverages them to transfer a leader motion to a follower one while maintaining the nature and characteristics of the follower. Notice how the output motion precisely follows the steps and rhythm of the leader while also incorporating the motion motifs of the follower. The term outline relates to what the character is doing and when. It provides a visual blueprint, if you will, for the sequence of actions and transitions in the motion. The term motifs relates to how emotion is performed. It includes subtle nuances, gestures, or patterns that convey meaning and emotion. For example, if we mixed the dancing motifs of the follower on the right with the circular outline of the leader on the left-hand side, we would get the result we've seen beforehand. We name our work Monkey See, Monkey Do, or MoMo, as it encapsulates the concept of directly transferring emotion outline from a leader to a follower while retaining the follower's unique motifs, much like a monkey mimicking observed behavior in a monkeyish manner. MoMo is unpaired, operates at zero shot, and does not require optimization or model training. Existing motion diffusion works overlook the profound potential embedded within the latent space induced by pre-trained models, and primarily focus on manipulating directly the motion space. Analyzing the profound potential embedded in the self-attention features, we showed that keys mainly encode motion motifs, while queries mainly encapsulate its outline. This visualization shows k-means clustering of self-attention keys. Note how when clustering key features, the unique motifs, such as standing, walking, or turning, are grouped separately into clusters. On the other hand, when clustering query features, periodic steps are grouped together and the start and end of motions are apparent. This indicates a dominance of outline features over the unique motifs. Our MoMo framework uses these findings for motion transfer. The input to our framework are two noisy tensors, produced typically from Gaussian noise or by inverting a real motion, and their associated text prompts. We initialize our output using the initial noise from the leader motion and pair it with the text prompt from the follower one. The three noisy motions are passed to the frozen denoising network at each time step t along with their prompts. During processing, we fuse the motions through mixed attention, combining the query from the leader motion and the key and value from the follower. Our framework offers a versatile motion transfer technique, facilitating various tasks of transferring motifs from one motion to another. One special case is spatial editing, where specific joints, like the arms, are edited while the overall motion is preserved. Another special case is action transfer, such as walking to crawling. Here, the leader and the follower motions are completely different, and yet the output still imitates the follower's actions, but in the same rhythm and leg order as the leader. Here is another example of action transfer, from jumping jack to jumping forward. Note, the outline in this example does not relate to feet rhythm, but rather to up and down submotions. Style transfer is a special case that refers to retaining the given motion while changing an emotion or physical state, such as happily or like a monkey. As can be seen, our style transfer retains the original action, such as walking, while encompassing changes to the whole body. In this example, the follower is the network's attempt to generate a dancing gorilla. However, this attempt fails to dance. By applying MoMo, on the other hand, we generate a person that dances in the same outline as the leader, but with the motifs of the gorilla. This is especially useful for out-of-distribution synthesis, entailing uncommon motions, posing a challenge to the network's generalization capabilities. Our work stands as the sole approach capable of utilizing motion DDIM inversion with diffusion models extending its application to both real and generated motions. How simple it is to utilize the provided follower motion, while how challenging it would be to generate a similar motion using text. To illustrate the necessity of latent space editing, we compare MoMo with its naive nearest neighbor equivalent. In our naive approach, for every frame in the leader motion, we calculate a similarity score with all frames in the follower motion. Then, we examine several approaches. In the first approach, we select each frame's nearest counterpart in the follower motion and incorporate it into the out motion. Since the extracted frames are not fused together, the result is jittery. The second approach computes a softmax on top of the similarity scores, extracting followers' frames according to the softmax weight. Although extracted frames are now fused together, the result is unnatural and exhibits artifacts such as foot sliding. In contrast, our result, using mixed attention, is natural and smooth. MDM inpainting generates motion for given parts of the body while preserving the motions of the rest. While effective for spatial editing, this approach lacks generalizability for broader motion transfer tasks, which typically involve editing the entire body. We test MDM inpaint with the upper body generated and the lower body kept unchanged. As can be seen, this yields a very unnatural motion. On the other hand, our result follows the same steps and timing of the leader combined with the running motifs of the follower. Here, we compare our work to a representative of the style transfer special case. Most motion style transfer techniques do not generalize well to unseen styles and typically require training, unlike our zero-shot approach. As can be seen, MOST struggles with inputs that are not strongly clustered into specific structures and styles. While on the other hand, MoMo easily combines the style of the follower with the structure of the leader, even for difficult cases. Thank you for your attention.